for those people who missed it, maybe so last time we just talked about the idea, what if space, space-time actually has real properties? I mean, we just talked about that really. And now we're going to continue with this idea. Well, if space has properties, what are the implications really, right? Is there anything that comes out that resembles general relativity? And next time we can talk about special relativity. So let's just see where this leads us, right? Are there any contradictions? Is this a consistent model or not? And just to refresh from last time, this is really the core thing, right? So even Einstein said space is endowed with physical qualities, and we were just trying to think about what that mean, right? And there are multiple aspects to this, of course, but one core idea is that, well, from general relativity, we know that gravitational waves are most likely transverse, and I'll have a slide right on that right after. And
Mhm.
also we know that electromagnetic waves are transverse. So from that, you need to have a medium that has shear elasticity to support transverse waves.
Yeah.
That's really the main idea. And if people understand just that one thing, I think it'll get us all the way to the end.
Yeah. And
um,
that really limits other media, right? So
yes.
it limits it can't be a liquid. I say the word liquid because I use the word fluid and, you know, there
Yeah.
there are things like superfluids and things like that that may behave differently than actual fluids. And so
Yes.
I try to be careful about what words I choose. It's definitely not a gas, definitely
Not a
not
normal gas,
a
not like
liquid.
yeah, not a
Yeah,
normal liquid. You would
exactly.
have to have really special properties. Like
Yeah.
even for a gas, like in theory, sure, you could have vortices, and the vortices could be considered elastic in a way, but that's like we make it really complicated. At the
Mhm.
end,
Yeah.
even if you have this special fluid or gas with water, it still ends up you need to have shear elasticity. However you want to achieve it. Otherwise, you will not have transverse waves.
Yeah.
Otherwise, you could have
Exactly.
vortices, but they're not waves. And vortices don't pass through each other unhindered, right? And we know from
Mhm.
light, it can pass through each other unhindered. So it needs to be something like a wave. And I don't want to make it too complicated. I really want to keep it simple. So I'm just looking at something that has shear elasticity, whatever it may be, whatever, if it's
Yep.
continuous or not, I don't know. Even just that alone, that's a simple idea. Is
Yeah.
it consistent? Because otherwise, once it is, right, we can always then go deeper and say, well, now we know that works. Well, what else can we conclude? Is there anything else we can talk about?
Mhm.
And the nice thing is that for any medium that has shear elasticity, the wave of the shear, so the transverse wave, is determined by the shear modulus, this mu here, and density. I know people have commented, I think someone was asking, why aren't you using this formula, with permeability, permittivity? And of course, that's also a valid formula. The thing is, it's special. It's really limited to electromagnetic waves. And I want to keep it general. I want to talk about any
Yeah.
kind of wave, whether it's
Yeah.
matter wave, a light wave, or,
Yeah.
gravitational wave. So I want to keep
Yeah.
the most general formula.
And exactly. And we did talk about that last time, and I did show you a couple of ways that we could rate the equation the
Yeah.
way you like it,
Exactly. Yeah,
where it
yeah,
does,
exactly. We can always map
it
it
does
back,
follow that.
right? Yes, we can always go back to this
Yeah.
formula.
Yeah.
So yeah, they're really equivalent, but this one is more common
Yeah.
used in material science. So
It is. Yeah.
because when you study, like to understand this medium, we need to kind of go to material science to understand, well, what happens to these waves? And it's, when you Google this, for instance, you will find lots of material on this, whereas there's not
Yeah.
much on this, right?
Yep.
So one critical question I can imagine people might have, and I have a small demo on this one, is, well, how do we know gravitational waves are transverse? Because I know someone was saying, I don't forget who it was, well, no, they're longitudinal. So this is an important question, and I researched this a little bit. So first of all, there are the multiple experiments that have been done on this, and it's kind of similar to the Michelson-Morley experiment. So you have this. I know this is a simplified visualization, of course, but hopefully it captures the main idea. So we have this, laser that emits light, just like for the Michelson-Morley experiment. You have these two arms, right? You have a mirror, reflects the wave back, and then you have a detector. And if nothing is moving, if everything is stationary, you would expect the waves to be, overlapping perfectly. There's no interference pattern at all, right? And now they have been doing this. And the thing is also, there's not just one experiment, like there are three different experiments, LIGO, Virgo, and some other one. Because it's important, right? You have to make sure, let's say there's noise, let's say there's a little vibration, a local vibration, like someone was hammering, right? the neighbor. Well, of course, then you could get some interference, but that's not, we don't want to detect that. We want to make sure we're actually detecting gravitational waves. So that's why these
Gravitational
experiments,
waves? So this is
gravi
for gravitational waves?
gravitational waves,
Okay.
yes. We want to make sure we are detecting actually gravitational waves and not some
Okay.
neighbor hammering some picture
So
frame,
this
right?
is like LIGO. This is like LIGO.
Yeah, yeah. And there are
Okay.
multiple experiments. They have slightly different orientation, right? So you can imagine when a wave comes in, on the one experiment, it might be this kind of motion. I can actually enhance it a little bit, see visual strain amplitude, just to exaggerate a bit. So let's say this is gravitational wave coming in. On the one instrument, it would be like this, and because the other instrument has a slight angle, right? It might actually look like this because it's at an angle. And you can do the calculation when you have multiple instruments like this. You can calculate, well, how much, what's the effect of each and the angle, and you can then calculate, well, what is it matched to? Because there are different possibilities, right? Because in principle, gravitational waves could be longitudinal, right? They could be
Hmm.
some kind of scalar breathing mode. Of course, the difficulty is if it's actually symmetrical, you couldn't tell, right? If it's literally, if here was the center, you couldn't actually tell. It could be longitudinal, something like this, and it could be transverse. And they did, and I researched this, so they did look at all these options and the combinations, right? And right now, the way it is they're certain that there is a transverse component, and they cannot fully rule out longitudinal components, but it's just unlikely. I don't know, the numbers depend a bit on how you calculate this, but it's approximately 2,000 times more likely that it is just transverse versus a mix. But there's still a chance, like, so the longitudinal component is not ruled out. But
Okay.
it looks
So
like
I think it was me. I was the one that said gravitational waves might be longitudinal last time we talked.
possible, but I think
So,
it's good.
and
It's
I
good to
was
question
modeling it.
things.
I was
Yeah.
modeling as a P wave. So as a P wave in earthquake science. So in earthquake science, you have the S wave, which is the shear wave, and you have the P wave, which is it has a tiny like transverse component to it, but it's much smaller than the actual
Mm,
big shear wave, right? So when you look at the graph of the device they use for detecting earthquakes. So the P
yeah,
wave
yeah.
is a little like wiggle, and then the S wave is like a big, giant wave.
Right. Yeah.
So I think, that's just where I thought that was would be an interesting analogy in terms of the medium, right?
Yeah, and it
Because,
looks like they did look at these things, but it's just most things in science are not 100% certain. But right now, the model fits much better for mainly transverse waves, and while it doesn't completely rule out longitudinal waves. So I would think, it looks to me like they did a reasonable job and did the calculations, properly. So I do think it's likely that they're correct. And so that would be one evidence to say, well, it's probably transverse, so we do need the shear modulus. And of course, similarly for electromagnetic waves, they're also transverse. So that's why the reasoning was about, well, we do need some shear modulus, right? That's just the reasoning that I was using.
Mhm.
So,
Yeah.
so the main equation to use here is literally just that. And we're going to be using this for general relativity and also for special relativity. So the wave of the speed is basically just the square root of shear modulus divided by density. So now you could ask the question, well, what happens when we have a wave like this, where the shear modulus is not necessarily constant, or the density is not a constant everywhere, right? And this is a new visualization I'm going to show with people. I have these funny videos with simulations with people also for the double slit experiment later on. And I think it makes it really easy to understand even for children. So you could actually do these
Oh, cool.
experiments
Yeah.
with a bunch of kids in a classroom. So imagine we have this cello-like substance, and this is just a picture of a transverse waves. Of course, I'm showing the surface here because we can't really see inside, but I don't mean surface waves. Okay, just I want to be really
Yeah.
clear.
It's
I
it's in
do
the
mean
bulk. It's in the
I
bulk.
do mean
Yeah.
bulk waves, of course, but to
Yeah.
see them often it's easier when you have a surface. Just to be clear,
Yeah. No, I
um,
understand. Yeah.
yes. So imagine you have these waves going this direction, following this yellow line here. You can draw like this blue line where there's a peak of the wave. And what we will call this is like a wave front. So the wave is moving in this direction as an example, right? And of course, so in some of the simulations, I'm abstracting this. So this line here would be the wave front, and this yellow line is the direction of the wave that's moving.
Propagation.
And so now we can do the same thing with people. So imagine we have a bunch of people marching. Let me just add more people because I think it illustrates it nicely. Let me just slow it down a little bit. They're marching on a lawn, okay? And this one line here is like a wave front. They're marching on the lawn, and now they're getting into mud. This yellow area is mud.
I like this. This is
I
great.
love this. This slows them down, right? Obviously. So, and then what happens now, if you look closely, and I'll restart it. Let me see, I maybe increase the gap a little bit, and then I'm gonna reset it to make it clearer. So now I increased the distance a little bit. Well, yeah, a little bit. So when you look at what happens, this line here, right, that's the wave
Hmm.
front. And now when you look at the line, what happens to that wave front after? Look, it's bent. It's curved now, even though
Hmm.
each person
Yeah.
still continues marching straight. It doesn't, each person doesn't actually make any change. It just, each person gets slowed down. That's the only difference. But the front line, like here's the line at this angle, and further down, you see a different angle.
Yep.
And if you
I like
understand
that a lot.
this,
That's
you
very clear. I totally get
understand
it. Yeah.
general relativity, basically.
Yeah.
Now, yeah, now we can also do this in a bent mode. This is like how your glasses work, right? When you have air and then you have a glass and the light rays are bent, right? We
Hmm.
can also do this in a gradient. So imagine we have this, let me just increase the lower speed slower so we have a more clear. So there's grass and then it gets just slowly muddier and muddier and muddier, right? You get slower and slower and slower as
Mm.
you increase the amount of mud. And what you get is this curve.
Yep.
And yeah, this is basically how you can imagine light waves bend
Hmm.
around, there's
In a
also,
gradient.
yeah, in a gradient, exactly. So because I think it's really, people learn this in school, but I don't think they always learn like why, that it's actually the speed of the wave slowing down.
Hmm.
And I can imagine people panicking. Oh my God, what did you say? Speed of wave slowing down. And it's all consistent, okay? It will work out all the way consistent. Let's see, we can also change the angle here. So of course, if it's straight, you wouldn't notice anything, right? But when you change the angle, it gets more
Mm.
pronounced,
Yeah.
right? Yeah.
Yeah.
So that's
And
that
the curve bends towards the normal of the gradient.
Yes, exactly. And
Right.
here
And I think
is a
that's an
little
important thing.
more abstracted version of this, where we have just, the wave fronts are just the lines when it's head on, right? You just see also what you notice is the wavelength gets smaller, right? You see
Yeah.
this compression, so the wavelength
Yep.
here is larger than here. Um, and with the bending, right, it's the same thing. And you can do the calculation. It's basically um, what we can do now. We can check, if how much do we have to change the density or elasticity to achieve a certain angle, as an example, right?
Oh yeah.
Yeah, yeah. Then I'll share the links to these simulations. It's usually more fun to just play on your own
Hmm.
with this. So this is the one I showed initially with James, and I wasn't sure if everyone really understood it, so that's why I thought
Yeah.
I will do another one. So here again, it's the
Yeah.
same
No, the
thing.
other, yeah, that is okay, but the people one is very clear. You get the sense that, like you say, you're walking through the mud, you get the sense that they're slowing
Yes,
down. You can see it visually in your visualization. So
exactly, right? Yeah,
yeah.
yeah, yeah, yeah. So yeah, and the interesting thing is this is not a new idea. So, which is
Yeah.
so fascinating to me that Newton even had this idea. Of course, Newton had a lot of ideas, but one of them is this. He thought that maybe the light bending around massive objects is due to refraction. So he did say this, doth not the refraction of light proceed from the different density of this ethereal medium in different places, the light receding always from the rarer parts of the medium, and is not the density thereof less in free and open spaces, void of air and other grosser bodies? Right? He got it
Yep.
exactly. It's
Yeah,
so
he had
amazing.
it. He totally had that.
Yeah,
Yeah.
yeah, yeah, exactly. And though this decrease of density may at great distances be exceedingly slow, yet is the elastic force of this medium B exceeding great, it may suffice to impel bodies from the rarer parts of the medium towards the denser with all that power which we call gravity. That's just the language,
Love
the
that.
power
I
which we call
know.
gravity gives me goosebumps in a way.
Yep. Yeah. Yeah.
And it's sad that
Very,
people,
very formally stated, nicely
yeah,
stated. Yeah. I like it.
it's too bad we don't learn this in school, right? Because, this is, people should have thought about this more. I'm like, yeah, this is so simple, right?
Yeah.
And I know people will say, there will always people will say, wait a minute, speed of light is constant.
Yeah. Yeah.
But
Yeah.
yes, it will be measured constant locally always. That's true.
Yeah.
But when you just think about, even when you like consider science fiction movies where they try to do it correctly, when you have these movies where a spaceship approaches a black hole, their time slows down, and there's everything slows down for them. When we watch someone in
If
a
you could.
approaching a
If you could.
if you could
Yeah.
approach a person approaching a black hole, for them they wouldn't notice a change, but we see them slow down. So there is a difference between
Yeah.
the clocks, and so it's the same everywhere. It does depend where you are in the gravitational field.
Mhm.
And also the idea of a refraction of a gradient is really not new. I mean, I don't even need to show the demo. I think there's these optical lenses that people wear, these glasses, right? There's a gradient where I think on top you
Mhm.
see far, and at the bottom you use them for reading. This is not new. There are also many examples of refraction for totally different kinds of materials and waves. So you get, for instance, shear wave refraction in Earth,
Yep.
even I guess if you had an
Absolutely.
earthquake wave, right? If there
Yep.
was
Yep.
the medium had different densities, you would
Hmm.
get this effect.
Exactly.
And it's always the same. It's just the same formula. You
Hmm.
get this for sound also, or for light waves in when you have the different air temperatures, because the different air temperatures they have also a result in different speeds, and this causes like these mirage effects, for
Oh, yeah.
instance,
Yeah. Yeah. Hmm.
right? You can get
Yep.
reflections and all that. You can even get it for sound when you call your dog, for instance, right? When you have cool air and warm air, and there's a difference in temperature, the sound waves may bend up or downwards. Um, so this is a well-known phenomenon, and it's very,
Mhm.
very simple. And you can even do this in your kitchen. So here's an example where you can actually do light refraction in your kitchen, where you can take a bowl of water, you put in
Yep. I've
lots of
sugar.
sugar.
Yep.
Did you try it? I think I
I've
have to
seen
actually try
no,
this.
but I've seen this experiment before, and it's one of those things I've always wanted to try, but I don't have a laser. So I
Well, I
guess you
guess
could just
for
use that.
talks, you could get these cheap laser pointers. We should. I do
Yeah,
want to
the
try
laser
it one
pointer, I
day.
guess, would work. Yeah, yeah.
And just what
Mhm.
you have to do, you have to make sure there's lots of sugar down here.
Yeah.
So don't
And you
stir
want
too
it to be a
much.
gradient.
Yeah,
Yeah.
you want to have a gradient. And so then, when you shine a laser through it, it will actually bend. So it's not
Hmm.
something totally crazy idea, it seems to me. Um, and also sometimes in the simulations, and also further down, I will use different terms. And this has confused people, but it's really all kind of the same. You can express this kind of change using refractive index, right? And that's really just expression of the ratio of the speeds of the waves. You can also talk about optical density, which is again the same thing. It's just using a different word. We
Yeah.
can talk about, of course, then we kind of talk about mass density, where we actually talk about the density of the medium. Now, of course, we don't know what the density of that medium is, but we know, both together. So influence
Yes.
mass and the shear modulus. Now, of course, what we can do is there are actually people using this in research. Um, you have something like called optical black holes, where you have a metamaterial, an optical metamaterial, where you change again the refractive index. And people have been using this, as the
Yeah. Yeah. I've
optical
seen this. Yeah.
analogy. Yeah,
Yeah.
right. And I do have a simulation on this also. So here is basically we have a gradient, right? Towards the center here, there's, more higher and higher refractive index. And in this case, the light beams, they're just, curving around. You can see the closer they are, the more they will bend. And then what we can do now, we can go near the photon sphere. And in this area, what happens? this is the area where the light beams start to go inside. They don't,
Yeah.
and it's more, it's not a black hole, it's not the event horizon, but
No, I know the photon sphere. Yeah.
oh,
Yeah.
okay, okay,
I've never
where,
seen a simulation of it though. This is the first time I've seen. See, the photon sphere, I'm a big fan of black holes, so I spend a lot
okay.
of time dreaming about black holes.
Hmm.
And so the photon sphere, when I was first looking into it, because I have a paper, the Mandelbrot set as a quasi-black hole, and that's another story we can get into some other time. But so I was studying black holes, and then I discovered there was a such thing as a photon sphere, which you never hear about. For some reason, no one
Oh,
ever really talk like very like when you talk about people talk about black holes, they go black hole event horizon. They never talk about the photon sphere, but the photon sphere is a very important region around the black hole as well. And so you're
yeah.
demonstrating this right here, which is very cool.
Yeah, and
Wow.
also I'm always questioning whether, theoretically, right, in the center, in the black, in the after the event horizon, there's supposed to be infinite density, and I kind of doubt that. I don't know whether we can if this can be proven or not, but it
Hmm.
seems to me just because mathematically you get this infinity, I doubt that in nature you actually get this infinity. So how do we know for sure, right? Because at some point the light rays that are going in circles, you won't see them anymore. So
Yep.
how can we distinguish really between a true black hole and one that's, almost a black hole, but there's no actual singularity because, you can
Hmm.
calculate this, right? You just need a certain amount of mass compressed to a certain, volume. And after
Yep.
that point, the escape velocity, if it's above speed of light, you will not see this. It will look like a black hole. I don't know if there's maybe some small differences, but it seems to me,
Hmm.
I don't think we should just assume it's going to be a singularity, right? That seems unnatural to me.
Yeah.
And I hope there's a way to distinguish because it just to me makes no sense.
It's I don't know. It seems almost impossible to know, right? Because we can't get inside a black hole to see if it's infinite density. If we did, we wouldn't be able to get back out again to tell anyone. So, that's a tricky one. I think in theory it could be infinite, but I think the universe has a limit, like the Planck limit, let's say, is the limit to the
Yeah.
digits of
Mm.
precision of the computer. And beyond that point, it's never going to be infinite, right? The
Right. That's yeah,
singularity
yeah,
might
yeah.
collapse to a certain point, and then the collapse will break down. I actually have a simulation of that in my Mandelbrot set as a quasi-black hole. I find the same thing in the
Mm-hmm.
Mandelbrot set as I do in black holes. And so, I think, I feel like there wouldn't be a infinite singularity. There would be a quasi-singularity that has an ending point,
Yeah, yeah.
right?
Exactly. Yeah. So now, of course, we can do this in 3D. And the question is, of course, well, how do we describe this? I'm not going to show the simulation because I think it's pretty clear now. But so how do we describe this curvature? And now this is where we get to the metric tensor, right? Um,
Hmm.
yeah, this will take a little bit of explanation, but I think it's good to understand this. So let's just start with I just call it the flat space-time. With that, I mean we have this elastic continuum, and it's just perfect, all right angles. There's nothing in there. There's no matter, no curvature. It's just completely, regular. So when you draw a grid, it's all right angles, right? That's it. That's what we would
Yep.
call flat space-time, I guess.
Yep.
So now let's say we can do stuff to it, right? We could stretch it, we could bend it, right, in different directions. So if I wanted to tell
Cool. I
you,
love that.
from a flat cello,
Yeah.
move to the third square in X direction, to the second from the Y direction, and how would you do that? I would need to tell you somehow how it was curved so you could figure out where to go, right?
Yeah.
And this is where the metric tensor comes in. Now, this is just a matrix. This is not a tensor yet, right?
Yeah.
So let me just start again from scratch. Change it to maybe I'll just restart it. It's probably the
Now
easier way to
there's
do it.
something over here obscuring on the screen, and I might just be on my end where I can't see the metric tensor very well. There's like
Oh,
some graphic.
oh, this thing. I don't know
Yeah.
where this is coming from.
Okay.
Yeah.
Okay.
So
It's fine.
and of
Oh,
course,
there
people
you
are like,
go.
oh,
Oh,
like,
good.
wait a minute, isn't that four-dimensional? We're just talking about three dimensions. I will get to the fourth dimension right
Yep.
after.
Yep.
So let's just look at
Good.
three dimensions now.
Okay, so I have a question about the metric tensor that you're showing, which I,
Okay.
saw last night when I was watching your video with James.
Hmm.
So is this the metric tensor, like you're just extracting the metric tensor from your medium, or
Yes.
did you design your medium to have a metric tensor? Or is it kind
You
of
don't need to design anything. All I'm doing here, so
you're just
let's just start from
reading?
scratch. Let's just forget about general relativity. There's no general relativity. All I have this thing, and I want to squeeze it, and I want to help explain to you how I did it, like what I did to it.
Yep,
So
yep,
then you can navigate. If I tell
yep.
you where to go, you know. So what we could do is we could write this down with numbers. So the diagonal are just in the x. It's just how much stretching we do in the x direction. So when I stretch it, you can see that first number here. That's the number that tells us how much we stretch or squeeze it
Okay,
in the
perfect.
X.
Yeah.
That's all that's doing, right? Same
Hmm.
for the Y. And so, Z direction. So if it's perfectly flat, it will just be ones in a diagonal.
Yeah.
And now what we can do, we can also twist it. And when you can see the diagonals will show up the twisting, how much twisting we have. And we don't need to know the details. It's just the amount of twisting can be described
Hmm.
by this
Yep.
matrix. Um, that's basically most of it. Now, of course, see this red dot here? This is in one plate. This is the how much twisting and stretching happen in this one spot here
Oh,
at
okay.
this
So
one
the metric
place.
tensor is associated with that dot.
This right now is just a matrix that describes the local curvature right here. So when I
Where the
move
dot
this
is.
probe,
Okay.
I can
Yep.
move this probe, I can move this dot around. And you can see how the
Okay.
numbers
Good.
change. Now, when I move this, now it's different because maybe here there's a little more stretching in
Yep.
one direction, more. So you have to imagine I put a sticky note. This is like imagine you put this on a sticky note,
Nice.
and I put this sticky note everywhere, thousands of them, everywhere, right? So there's a sticky note here, and then one here and one here. At each point, it tells you, oh, how much is it twisted or stretched or curved. The
Cool.
whole thing is the tensor. So all
Okay.
the sticky notes in this cello, that's the metric tensor because that tells you everywhere like how much bending and curving and stretching that we have.
Okay.
So that, and we can also show the grid. So basically, yeah, at each place where we put this red dot, we have the sticky note. So the sticky note here, this tells us, well, there's the x coordinate is almost flat, but then there's a little bit of stretching in the z direction and so on, right?
Mhm.
That's all it is really so far. So that's the metric tensor. It's nothing, you can use it for any material. You can use it for rubber that you're bending, and if you want to explain to someone what does it look like, you could basically tell the person, well, take a cube, here's the metric tensor, and they could then draw it, right? They could then say, oh, I know exactly how it's curved and stretched at every point. Basically, that's the metric tensor. That's all it is. So it's nothing magical. It's just, it's just
Mhm.
a way to describe how to shape something, some solid material, really.
Yeah.
Um, but now, of course, we haven't talked about time. Is this the one? No, this is one I was just showing the same thing. Yes. Oh, yeah. And Chris from Dialect, he has some very good videos on this also. He has really, really great animations. So I encourage people to watch those.
Okay.
He explains, how it's just like a map, how you basically have, let's say, a map that we have when you go hiking, right? It also has, the scale, for instance. You need to know how to get from one spot to the other, but then you map it to the real world. So oh, if it's 1 centimeter on the map, oh, I actually have to multiply it by some factor, right? And also, we draw maps flat
Yeah.
and the Earth's curved. So we also kind of need, of course, for us it's easier, but it's a similar kind of thing. It's just like a map that tells you how to get from this map to the curved map, basically.
Oh, I see.
Um,
It's a mapping, literally. Yeah.
Now we need to also think about, we haven't talked about time, right?
Yeah.
So let me just, oh, actually, I just did a simulation today. You know what? I'm going to show this. I actually wrote it for special relativity, but no, it's okay. No, I'll show that later. So what is time? The thing is, time is usually something that moves. Like imagine we had a clock that is composed of light, right? So this could be we call this a clock. So we're just
Yep.
saying when we have this laser here, there's a mirror. Once it goes up and down, that's what we call one click. But it is one of our seconds. That's just how we build our clocks, right? And what I can do now, well, this speed, of course, is determined by the properties of the continuum. So density and the elasticity, right? So the denser it is, the slower this clock would move, this light beam
Yeah.
would move, and so on. So you could imagine that the speed of that clock would change if we changed elasticity or changed density. And that's really all the magic there is. So the question is, well, how can we measure that time, right? And last time I said, well, we watch from the outside, and people didn't really understand what I mean. So I'm just saying, let's imagine we have two people, right? One person, let me just go start this demo. One person is really, really far away and has that clock in flat space time, okay? And the other person is in an area where it's curved. So this is what I mean with this. So there's this one
Right.
person, let me just use the light clock. So we have two people. One is really, really far away. And of course, I can't draw it. So I'm just moving the clock closer so we can see the difference. But you have to imagine this person is also in the same jello,
Okay,
right?
so it's far away from the curvature, is
Yes,
what you're
it's
saying.
basically
Yeah.
as flat as possible. So we have
Yeah.
right now both are in a flat space time, right?
Yep.
We have it's all flat. The
Yep.
two clocks there, but this is also inside a cello. But of course, I put it there because I want to compare, right? So
Yeah.
this is what I meant with outside view. And people say, hey, you can't be outside the universe. Yeah, of course
No,
not.
it's just outside the gradient that you're going to be building.
Yeah. And of course, me
Yeah.
as a developer, like, I mean, I have a computer simulation, I could watch it there, but it's fine. Let's pretend both are in the universe. This one is just really far away in a flat space time. And so this will
Yeah.
never change. This will always tick at the same speed. And this one, now we're going to do something to this part of space time, right? So
Yeah.
what we do, and again, this is the probe position. So, we could put the clock anywhere in here. We could stretch it, we could compress it a little bit, and when we compress it, we change the density, right? So now you can already see it got more it slowed down a little bit
Hmm.
because it's denser. And remember, the speed of the wave depends on elasticity divided by density,
Yeah.
so the square root. So when we make it denser, it will slow down, and that's what we see here. So now see the matrix here is now
Yeah.
four-dimensional. And these are
Hmm.
just these three here. So this part described what we saw before, how much
Yeah.
stretching we did. We didn't have any curvature, it's just compression right now. And this number, all it means, well, how much did the clock slow down? That's all it is. So if we, stretch it, if compress it further, the clock will slow down further. Why? Because the speed of the light wave will slow down. That's all it is. Because in a denser medium, or if it's less, more elastic, less elastic. If it's less elastic, it will slow down, basically. Do you think this is clear?
Yep.
Okay.
Oh yeah,
Because
it's clear to me.
yeah, because
I
there are always some people who don't
I've
see,
cheated though because I've watched the video a bunch of times from James, but um and I made sure I understood it. But I totally get it. If the density is higher than the the way the formula is, it's going to slow down the speed of the wave, of all waves, of all phenomenon. It's going to slow down all phenomenon. You have to assume that that clock that you have in there is a light wave that's bouncing or whatever. If it is, then that is definitely
yes,
going to slow down. And so,
yes.
yeah,
So of
I,
course, this would
I
not
totally get
work if clocks were not waves. This, of course, means that in this model to work, everything has to be a wave. So the clock
yeah,
has to be a wave.
yeah,
Measuring sticks are waves. Even your
yeah,
mechanical clock, when you zoom
yeah,
into it, right, there are atoms and atoms of
exactly. And
electrons, and
atoms are
electrons are
waves.
electron
Yeah,
waves.
yeah,
Protons are little waves. Everything has to be related to some kind of wave. And that
right.
maybe that's the thing that people find difficult to understand,
Yes.
that
How
a
can a
clock is a
particle be
wave.
a wave?
But when you
And yet,
zoom
and
in,
yet, and yet we have wave particle duality in the standard language. And so, by now people should be used to thinking of particles in terms of waves. But
yeah,
yeah,
electrons, Schrodinger equation, it's all based on waves, right?
yeah.
Even though people, imagine they're particles, but they're always described as waves. And we'll have another,
Yeah.
another talk on
They're
this.
basically localized waves. They're
Yes,
localizable waves.
yes.
Right?
And basically,
Like John Macken talks about. John Macken talks about having a laser, and when you localize that, the wave, when you localize a wave, it actually has mass. It can have mass. So he talks
yeah.
about that.
Okay. Yeah, and that's really all we need for the explanation why time slows down. And so there's nothing weird about it. It's not like, oh my God, it's four-dimensional. All it means, we have a number that tells us how much slower a mechanical clock is ticking.
Yeah,
When watching from far away, so we watch like this is a person far away, and there's this spaceship approaching a black hole, and their clock, from our point of view, looks like it's slowing down, but they wouldn't notice because
yeah,
for them, everything they couldn't tell because they have no reference, right? They what they could
yeah.
see though, they would think like our clocks are running faster. That's what they could see. They could see what's happening, these the stars out there, like we are approaching a black hole, and then if you would
Hmm.
look out you would suddenly see things moving faster because outside the time would appear to run faster than for you yourself locally, right?
Yeah.
Yeah.
Also, when you're increasing the density, does that change the size of the clock, the
Yes.
dimensions of the clock?
Yeah, that's a good question because see, when it would change to remember the marching band, when you have a wave front, when it goes into the mud
Hmm.
and the people slow down, the distance
Yeah.
between the rows they get smaller, right? So you get that
Yeah.
compression. Yes,
Hmm. Okay.
exactly. Yeah.
Yeah.
Things would shrink. They would have to shrink based on that amount
Mhm.
of density. Yeah.
Now, we could say something like, this is something I kind of like to say about light,
Mhm.
is that light propagates 1 unit of space in 1 unit of time. And
Mhm.
so if you're
Mhm.
compressing those units of space and units of time into a smaller region, it explains why it's not really slower. It's still light is still propagating 1 unit of space in one
Yeah.
unit of time. There's just more units of space it has to go through compared to the outside world to get to the other side, say, of the medium, right? So it
Yes.
appears to slow down,
Mhm.
but it's not slowing down because light propagates 1 unit of space in 1 unit of time. And when you're increasing the density, you're changing the unit of space and the unit of time.
Yes. Yes. Exactly. Exactly. Yeah, so that means basically that we are just looking at the mechanical speed of vibrations that are changing. And that when we talk about time, it's not literally time. So you might wonder, like, does time as a dimension even exist? I mean, it seems to me
Hmm.
time is really something we derive from movements, from changes. I wouldn't call it a separate dimension.
Yeah,
I mean, you could call anything a dimension. I could call color a dimension, but that's not really, it's not the same as like a spatial direction. It's really
yeah,
something that comes out of it from the speed of light.
yeah. Yeah,
Um,
I'm not a big fan of the use of the word dimension. Like that word is kind of overused and it's become
yeah,
a
and
bit
it's misunderstood.
ambiguous.
Yeah, because it makes everything look so complicated when it
Yeah.
really isn't. So now what we can do, we can play with this, and we have this light ray. It's just a light ray going through. And of course, this is not a perfect calculation, okay? This is just
Hmm.
an animation. And because if you want to do this for real, you need more compute power. But it still explains, what happens as we change the gravitational. I'm just changing, I'm creating a localized spherical density increase here in this
Oh,
example,
I see.
right?
We're in the middle, right?
In the middle, yeah, yeah, it's kind of
Somewhere.
hard to see, but just to
Yeah.
illustrate how a
Okay.
light beam would start to curve round. So
Hmm.
there's a refractor, there's basically a gradient. So far outside, it would be flat.
Hmm.
And further inside, you can see the light beam bending, and also the clock would slow down. So this is
Hmm.
close to the center. So when it's perfectly flat, the light beam would be straight. The clocks tick about at the same speed. And then as I increase the density, or reduce elasticity, right? This doesn't really matter which one. Then you would get this gradient, and the light beam would start to curve around more and more until it's. But so this last time, I think with James, I said black hole. It's not really a black hole. It's
Hmm.
just there because
Yeah.
I don't have a point that's infinite, and I didn't calculate
Yeah.
at what point the velocity escape velocity is fast. But it's something, a massive object. Let's just say a massive object, then we can increase this arbitrarily, right? And you can
Hmm.
see there's even a point where the light beam doesn't even escape anymore, so it will
Yeah.
start to cross that photon sphere and start to curve, inside. And at
Yep.
that point, it would look really dark, probably, close to a
Hmm.
black hole, I imagine.
Yep. Actually, my Mandelbrot set as a quasi-black hole has a similar thing, and the trajectories look just like that.
Oh,
They
cool. Yeah.
spiral in. They spiral
Hmm.
in, and they
Hmm.
spiral in like theoretically forever, but they break down at the limit to the digits of precision of the computer. And
Yeah,
so
yeah, of course. Yeah, that also.
you're never going to be able to like go forever
Yes,
with a computer, basically.
right, right. And here we can see again
But
the,
I'm thinking that the universe has a similar limit, and that's the Planck limit.
I think it makes sense. It would be interesting to see if we could go beyond that, you know.
Hmm.
But that would make sense, yes. And here you can see in this example, I have my probe in the close to the center, I think.
Hmm.
You can see the speed of the clock. It's not zero, right? It's still 0.01. So it's
Hmm.
100 times slower in here right now than on the outside.
Okay.
So the clock is still
Hmm.
ticking, but very slowly, very slowly.
Yeah. Oh, I see. Yeah. Hmm.
Mhm.
Yeah.
And what's also interesting, there's a lot of other things associated with general relativity. For instance, that when you have a light beam, let me just start that demo, that imagine we have, just emit a pulse from one side that has near a mass, so near like a sun or a dense object, and it's going further away into space where there's less mass. Okay, so it's
Hmm.
less dense, or the refractive index is different.
Yeah.
Then the light beam gets stretched. So
Yeah.
you have the redshift, and the other way you have the blue shift, and that's again something that we know, right? We know that
Hmm.
when a light wave is trying to sort of escape a gravitational well,
Yeah.
it gets redshifted, and the
Yeah.
other way it gets blue shifted. So all this is just coming out from that super simple relation that the light speed depends on the elasticity and density, and that's it.
Hmm.
Everything.
Yeah.
I'm not adding anything complicated to this. This is all literally by almost elementary school, right? So,
Are you familiar with the work of Halton Arp? Have
oh
you heard of
yeah,
Halton?
yes, I
Right?
am.
So
Mhm.
his theory, he was trying to explain exactly what you're showing right here. And he was saying that the quasars that we see that are like supposedly super massive and really red shifted, that the red shift is an intrinsic redshift, he calls it, but it would be a gravitational redshift, and not a cosmological redshift. So these quasars, he kind of discovered that they were local to the galaxy, that they were physically
Yeah,
near,
yes,
instead of being like billions of light years away. And
yes,
so,
that,
and
yes,
he showed
yes.
a lot of evidence of that. And
I actually, yes, I
no one really,
totally, people should
yeah,
talk about him more because I think
yep,
I have a book even, I read it, and I'm convinced there's something to it. I think
yeah,
people oversimplify the whole thing with expansion of space-time and all that.
mm,
And I do have actually episode 11 on where I talk about this a little bit because I think people do need to revisit these things and
mm-hmm,
question the assumptions because
yeah,
it was many years ago. I on a forum I asked a really naive question. All I asked is, how do we know that the redshift we see is 100% from space expansion? Maybe it's 80% space expansion and 10% gravitational. Maybe it's
yeah,
5%
mhm,
something else. And then I was like, oh, crackpot, right? So I'm like, what?
yeah,
I asked
no,
a normal
I'm,
question. And this made me really suspicious. This is actually one of the reasons I started getting into this because I'm like, you're always supposed to be able to ask questions. How do we know? And the thing is, there's no answer really. I think people just assume all the
yeah,
redshift is space expansion. And I think that's
yeah.
just not that,
I
to
don't
me,
think
it's
no.
like a
And
lot of
I,
red flags.
it just the evidence I saw that Halton Art showed, definitely the quasars do look like they emerged from the galaxy. And then he showed that the further the quasar gets from the galaxy, it's like it evolves into a normal
Yeah,
galaxy the
that's
further
really
away it gets.
interesting.
And he showed
Yeah.
many examples of this. And I
I
looked
know, right? It's
myself.
not just one statistical
Yeah,
fluke. There are
yeah,
hundreds or even thousands of them. And
mhm,
you can even see the material, like you can see
yeah.
the band between them. So
The
it's not just
almost, yeah, and you
random.
can almost see some of them like it's almost like an umbilical cord that's attached the quasar to the, it's like a birthing process almost, right? And
Yeah,
so
yeah,
I found that really
totally. I think it's
interesting.
really fascinating. I think we should talk about maybe after all we could to talk about this more also,
Hmm.
because I think people need to start revisiting those questions and
Yeah,
assumptions and um, yeah, definitely, definitely. So clearly, there's the one part of the redshift can be explained by gravitational effects. And the funny thing is, just was it yesterday in the newspaper or a few days ago, I saw that there's a study that shows that the Earth is in a local void. I think it's
yeah,
like 2 billion light years
yeah,
across, but I don't know if it's
yeah,
exact. But if that's the case, so if we actually are in a local void, that means light has to basically get out of this gravitational well I was just showing to us.
Mm.
So that would definitely be part of the wave.
Interesting.
Maybe not all of
Interesting.
it. I mean, to be
It
like,
could
it's,
be like because we only have our perspective from Earth,
yes,
and we
yes,
look out and we see that everything's redshifted. Could it be
yeah,
because we're in a local void? And that
yes,
would
yeah. I
be
was just asking
uh,
the question. I'm not even claiming
that's a
anything, but people
very
should look
good
at that.
question. I'm gonna look into that.
Even
It's
if
really
it's 5%, maybe, who
yeah,
knows, maybe there's still
yeah.
space expansion, but even if it's 5%, it will change the model, right? Because
Mhm.
all the calculations depend on that. So, yeah, anyway, I think it's important to keep asking that. So, um, now, of course, the question is, well, how does matter change that? Well, so because matter is supposed to bend, right? Change this the dynamic. It's supposed to change the density and elasticity. Well, how could that work? Now, that's important because we need to understand how that works. And this is from Marek Danielewski. So he has been working on this. I won't go into the detail here, but the idea is the main question is what is mass? And in this model where there's an elastic continuum and everything is waves, so everything is just
Mhm.
something jiggling, even
Yep.
mass, also matter included, then what's the energy? Well, the energy in that sense would then be a combination of the kinetic energy. And here's what I mean. So here I have this it's just sort of a slice and I have some vibration in here. It doesn't even matter. And I highlighted one red point. It's like a
Mhm.
pendulum, like this one
Yep.
grid point goes, it moves up and down. And just
Mhm.
like in a pendulum on one end, it stands still for a moment, but it's a lot of compression right here, right now, in this case. And it goes back to the other side. It has a lot of velocity. And then again, it stops here and then it reverses. Just like in a pendulum, you have just a change between the kinetic energy and potential energy. So
Yeah,
here you have a
exactly.
lot of kinetic energy, but no potential energy because for a moment it would be flat,
Yeah.
right? Back and forth. So we have different kinds of energies in an elastic continuum. You can have the kinetic energy. That means literally like the whole medium moving locally, just locally. Then you could have
Yeah.
compression momentarily, right? You could have
Mhm.
twist. That's all energy, right? You could have twist energy and then release it. There are all kinds of different motions you can imagine. So maybe what we call mass, and we know that mass is equivalent to energy. Maybe all it is just for a given volume, you sum up all the different energies. Well, we have some compression energy and some twist energy, and at the moment there's something wobbling around. So the whole
Mhm.
total amount of energy, that's what we call mass. I
Right.
mean,
Yeah,
this,
because in E equals MC squared, it doesn't say whether it's kinetic energy or potential energy or like that E is
yeah,
kind of ubiquitous, right? And it has to be a total energy. It can't be like, oh, it's just kinetic energy or it's just potential energy, right? It has to
yes,
be
yes.
a total thing. So that's interesting. Yeah. Yeah.
So, and then we can ask, well, so what is matter? Of course, we have a total separate discussion on that, but this is just a visualization. I'm just have because light waves are basically transverse wave that move, but a matter wave would be something that's kind of localized in some way. I'm not even speculating right here. All I have here is a spiral. I just have a wave going in a spiral. That's it. And
Okay.
what I've done here, I've added a refractive index. So it's a gradient from left to right. On the left side, you have a higher refractive index than on the right side. And all I'm doing is just calculating how the wave, as it goes around in circle, how is it bent and curved as in this gravitational
Mhm.
gradient, in a sort of
Yeah.
refractive gradient. And this doesn't even mean has to be, for general relativity specifically. It's for any kind of could be a glass, with with
Mhm.
a with a gradient, and you have a wave spiraling around.
Yeah.
And what you notice is that the center of mass, so the center of this will start to gravitate toward
Oh, it's moving.
slowly, yes. Of course,
It's
there are
moving.
details that have to be calculated, but the
Mhm.
principle, basic principle, is that because of this gradient, and because if matter is waves, the wave would start to move towards the
It would
oh,
naturally
yes,
gravitate towards the
yes,
higher refractive index.
exactly. So for this to work, that means would be an indication that matter has to be a wave, basically.
Yeah.
Yeah, because it's just if you imagine a light wave going in a circle, right?
Mhm.
If you did that and you just did the calculation, you would slowly go to the left in this case.
Mhm. Interesting.
Yeah.
So that would explain the slow gravitation of particles towards a
Yeah,
gravitational
exactly.
field.
And
That would
yes,
easily explain that, actually.
yeah, and there are papers about this. So Robert Close has written a paper. If anyone wants to read them, I'm not going to do all the math. That's not what I like to do. I like to do visualizations. So, but there are papers people can read with all the
Good.
details in it. But I don't think it would be super exciting to go through that. Um, yeah,
Too
yeah,
much
yeah.
math.
So I do have some more visualizations. I forgot what this was. No, I don't need this one, but this one there. Oh, this is another one here. Basically, Robert Close has done some work. Let me maybe show the formula first. Is this the one? Yeah, yeah. So he has written a paper about this, and he also explains the formula how energy, which basically means how much you have more energy, basically more waves, right, in a location, how it changes the property of the medium. So it changes
Mm. Oh,
both, based on, of course, we don't know for sure, right? But based on material science, so there's publications from material science that show when you have some medium and you increase the energy in that medium, like say rubber or whatever it is, um, then it changes not only the density, but it also changes elasticity. There's this relationship here. I think I do have this. It's not really that important, but it's just,
no,
I think,
it's good to know that when you change one property, it changes the other. It's not like you can just
yes,
change, you
exactly.
can't just change the density and expect the shear modulus to stay the same.
Exactly. So these are the two papers. If people want to read it, I can also add the
Okay.
links, that describe this. This is actually an old paper here. This is
Mm.
really like 1980 or something, or even older.
Wow.
Yeah, yeah, yeah. So say they already studied this in materials that when and you can imagine an analogy would be if you take a rubber band and you start to twist it, right, around and around, it would tend to get shorter, like the density would
Mhm.
increase, but
Yeah.
then it might not be as elastic anymore. So it will lose some of its elasticity as
Mm.
keep doing that. As you keep twisting and twisting it, it will lose some of its elasticity. And there's apparently a
Oh, yeah,
relationship
yeah, I can see
when
that.
you
Yeah.
when you increase the density, you also change. So here the x-axis is density and the y-axis is elasticity. You lose some of the elasticity as you increase the density. It might
And
it,
that's
that
according to that formula that you showed
Yeah,
me.
exactly. And of course, that's not a proof that it's the same in the universe, but it's a good starting point.
Hmm.
If their relationship is known, that maybe it would explain. It would make sense to say, let's look at that if that's the case also for the universe, right? So that seems like a logical thing. Um, and so then the question is, I'm not sure if I'm going to go into detail here, but there's always this question about, well, what about how is this the same, right? We have the inertia versus gravity. Now, a localized particle, if we consider this as a wave packet with this amount of energy, right? Then there's the question as you accelerate it, right? There's this inertia.
Hmm.
And what happens when you accelerate it? Well, you have this whole energy in this medium, and you have to start to move that whole energy somewhere else. So it takes, you can imagine that it takes work, right? And there's a resistance there to
Hmm.
change this vibration to another look to accelerate this. And I'm not going to go through the details because Robert Close has the details here, but when you do the math, it's the same explanation as you get for gravity. It's the same thing that the curvature of gravity, the calculation using the mass, it turns out to be the same. It's all about the energy, how the energy determines the resistance of being accelerated and so on. So you actually get the same thing. And so it makes sense that these are related, right? Inertia versus gravity, that there's a relationship there. I don't remember
Okay,
what
so
this.
inertia and gravity are two sides of the same coin, or they are the same
Yes,
coin.
exactly.
Yeah,
It has to do with the fact that what we call mass is really the wave
inertia.
energy in a certain amount of volume. And that wave energy is really vibrations of some sort in this elastic continuum, right?
Yeah,
And there's some resistance to that, right? When you want to change that, there's a resistance.
right.
And that's what we call, I
Hmm.
guess, acceleration.
Okay. Yeah, makes sense.
Yeah, I think. And so this is kind of the summary of this. Let me just move it over here a little bit. And yeah, when you look at the math, you really can see that the refractive index that you can calculate from all this corresponds to the gravitational potential, right? Sometimes you see this. I do have a demo here.
Hmm.
Now it takes a little time to compute. This one is a little bit slow. Maybe just to let calculate a little bit. Um, it's related. You can plot, like if you plot the acceleration, for instance, and you plot the refractive index, it's really equivalent. So it's a really one-to-one correspondence. And of course, there are some other papers. So the one of the big proponents of this, or one of the people who had the ideas, actually, I think Robert Close based a lot of his work on Hagen Kleinert. I think he didn't
Hmm.
even know about Newton's idea either. There's a paper by Hagen Kleinert who said talked about the world crystal. So he's really a material science expert, and he showed that this metric, the space-time metric, the Minkowski space-time metric, is mathematically equivalent to a model with a crystal. So he called it a crystal, and he showed that there's one-to-one mathematical correspondence, right?
Right.
And this kind of, started the ideas going for a lot of other people. So there's other papers, Ilya Schmelzer, Marek Danielewski, Robert Close, they've taken up this idea and written about this. So there's quite a bit of material. It's just, I wish more people would look at this. And it's not that difficult. The idea, it seems to me, is really, really, really simple. So here I have an example of the gravitational potentials. I have the 3D view here. So this is just the mass of the sun compressed to 2 kilometers. I just did something because otherwise it's kind of flat, right? It's not very
Yeah.
interesting. So I compress it to 2 kilometers. And 3D view where you can see the gravitational potential. And here, I don't know if it's big enough to see, but you can look at things like here's the potential here. So in the center, you have the largest potential. You can also calculate the escape velocity. In this case, because it's 2 kilometers, he actually goes above the speed of light in the center here. um, and this is the refractive index. So you can see that the refractive index is just flipped. So here we have the biggest refractive index, which corresponds to the lowest gravitational potential. But it's
Yeah.
exactly,
So they're inversely proportional to each other,
yeah, exactly.
technically. Yeah. Cool.
Now, I have also there are some people who like other kinds of visualizations. So some people say, oh, they like the flowing space or river model. And I
Mm.
think people need to be aware that it's a nice visualization, but
Hmm.
I don't think people should take this literally because, so what you can do, right? Once you have calculated this gravitational potential, you can calculate the acceleration everywhere, you can calculate the escape velocity everywhere. And
Yeah.
of course, what you can do, well, escape velocity, let's just reverse that and plot it, and it looks nice. I mean, I don't have a great visualization for this,
Yeah.
but
It's a good analogy. It's a
it
good,
looks nice.
it
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 looks
maps
like space is,
perfectly.
yeah,
You
yeah,
can map it
mathematically,
Yeah.
it's a one-to-one
Yeah.
correspondence. It's exact. So yeah, of course, with math, you can always do a lot of
Hmm.
cool things, You can take some number and visualize it in some way, but that doesn't make it actually a mechanical model.
Yeah.
The thing is, some people seem to take it as an actual mechanical model.
Hmm.
And the thing is, I see a lot of problem. If you actually want to literally take this, the problem is,
Hmm.
for instance, just some of them, okay, where does the space go? That would mean you would actually lose space, right?
Yeah. Hmm.
Where does it go? And then where is it coming from? Because is it, space being consumed for millions, billions of years? And then what? And then you need some mechanism to create it. Well, how does it, what about, is it equal? Like you always have the same amount of space?
Hmm. Yeah.
How does that work? You need another dimension for that then? Where is it?
Hmm.
Because if it's going somewhere, well, where is it going? What's happening to it? Why isn't the matter also sucked in? Why
Yeah.
does the atom stay there, but the space goes?
Exactly. Yeah.
There's so
Now,
many
this
questions.
is interesting. Like I was really intrigued when I only really heard about this like a few weeks ago, this particular river model
Hmm.
when I watched whoa, sorry, what's the name of the um
Yeah.
Henry Henry's
Oh, yeah, yeah,
stuff.
yeah. I have argued with
Yeah,
Henry.
yeah, yeah,
I've
yeah.
been trying to convince him.
Yeah,
So
yeah, yeah, I figured.
yeah, yeah. Of course,
He
yeah,
met,
yeah.
yeah, he mentioned you, so I figured you guys knew each other. Anyways, so, but there's another independent researcher named Robert Distinti who you may not know about,
Mm,
but I know my audience does know about Robert
okay.
Distinti.
Mm,
And so he had a similar idea He wasn't saying that space is flowing, but he was saying that ether. So
Oh,
he was
sure, yeah.
is
But even
ether,
if it's
right?
ether, right, whether you call
Right.
it space or ether, it's
Yeah, and
still the
so
same
he
issue.
basically, in his sort of logic, he's saying that matter consumes ether to stay alive. That matter is not a perpetual motion machine, but that matter needs to consume ether in order to, persist. And so that would explain, that doesn't explain anything, but it's just other people were thinking along this lines and calling it ether. And it's also almost like ether is like the food for matter, and that matter is not a perpetual motion
Yeah,
machine.
but then,
It
Michael, I have so
requires
many
the,
questions. I have like already 100
oh, for
questions in my
sure.
mind.
There's lots of questions, but I'm just saying, like,
How,
are other
where is it
people,
coming from? Why would,
right?
because
It had,
if
you
you
would
have
think you would
some,
run out of ether. Eventually, the matter would eat all the ether. That's what, my
yeah, and
problem.
also why, like, what's the mechanism? What is
Yeah.
matter then in that model? Because, like, for instance, I think Henry also thinks that the space-time continuum is elastic, and he does think that, I think he has done another video where he says that, light is a wave and matter is also waves, right? Now, remember the whole thing, what we derived, the only assumption we made is it's elastic, shear modulus. And from that alone, you already get refraction, right?
Yeah.
So
Yeah, you
now,
don't need this extra complication.
yes, even worse. Let's say for a moment, we look at this model. Okay, fine. Ether or space, it's being sucked in the center of the sun, whatever. Well, that means because if it's getting sucked in, you would expect some kind of compress. It would be more. There would be as it flowing in. You would change its density, right? Well, that now adds to the density on top of the fact that the space is consumed. Now we have increased density, which means you get refraction. Well, now you have to
Well, it
balance
could
it
be it
just
could be
right.
that the this is the mechanism for the increased density. That could be this is the
Yeah, yeah,
mechanism
but
for one and only.
the point is
Right.
that the inflowing space is already the mechanism in this model. But now on top of that, you also have refraction. Now we have two effects. You double the effect,
Hmm.
right? So now it has to be balanced just right that you have some consumption and some refraction. Now you have two models for the same thing. You
Hmm.
have refraction plus the on top of this, you have this space destruction thing, ether destruction. So it's just there's just making it so complicated, and I don't see why. Like, why would you? I mean, I'm not saying
Right.
it's wrong. I can prove it's. I cannot prove that it's wrong because you can never. I
Right.
cannot prove there's no big unicorn that's invisible either, right? But
No, but
it
you're
makes it
looking
so
for the
complicated.
simplest solution,
Simplest
and this
solution.
complicates it. This complicates it.
I don't see any additional value for explain. It doesn't
Hmm.
explain anything else. It's just it looks nice, sure, but it doesn't explain anything. You have all
Hmm.
these mechanisms. You need an extra dimension. You need to explain how mass doesn't get consumed with it, right? And also, then you have if you have a black hole, right?
Yeah.
Then the problem is that space would be flowing or ether at superluminal speeds. How does that work? And it's
Well,
just
no one said that space can't go faster than the speed of light. They only said that a
yeah.
wave in space can go faster than the speed of light.
Still, it's
Right.
weird. It's just, yeah, to me, it's fun as a visualization, but I don't think,
Because the expansion of the universe also has the same problem. If
yeah,
space
I
is
do have a
expanding,
yes, I do have
that
a problem with
and
that. Yeah.
they also say, there's no, it's not a contradiction because, you know, only a wave propagating in space cannot go faster than the speed of light, but that doesn't say what space can do. Space can,
True, but I
that's
actually have a problem with that as well. I have my hesitations there as well because I think it's weird. I
Mhm.
think at least part of the redshift I think has another explanation, maybe even all of it. So I don't know. That's probably a different discussion because it's just there are a lot of inconsistencies there. Also with the recent Hubble tension, there are all these problems. All galaxies, that get discovered that shouldn't exist. So I think,
Exactly.
I see a lot of
There's
challenges there.
lots of now that we're seeing more than we ever saw before. We're seeing every day I see, oh, another contradiction, a black hole that's too big, or, so many things. Well, we have to rethink things, right? So,
Yeah, yeah, exactly.
yeah.
And another thing is, in this model, right, you can imagine the reason for feeling the acceleration is because of that inflowing space, right? So you have to
Mhm.
work against it. So that's sort
Yeah.
of the explanation. But we know now, but the thing there's a difference though, in the center of the Earth, right? In the model we just talked about, and that's also the common general relativity assumption is that if you place the clock in the center of the sun or the earth, it would also run more slowly because there's a higher gravitational potential, right? Right in the
Right.
center. But in the center, there's no acceleration at all. You're actually weightless in the center of the earth, in the center of a black hole, if it could exist, right?
Yeah.
In the center of a black hole, you would be, free floating. And if it
Yeah.
weren't crushed,
There would be no
no
forces.
acceleration, but there's a really, really great gravitational potential, right? So the
Yeah.
clocks would be ticking really, like your clock relative to the others would be ticking really, really slowly, if at all. But if this were an actual mechanical model, then in theory, well, if there's no space flowing in the center, why would the clocks run more slowly, right? So this seems to be a contradiction, maybe not, but it seems to me when I look at this, you would have to explain why the clocks would still be ticking much more slowly in the center, even though there's no much space flowing there, right? Actually, yeah. Anyway,
Yeah, I see what you're saying. Yeah.
lots of
Mhm.
questions, and
Yeah.
as you were saying also, I'm just looking at the simplest model. Once we have it all worked out, sure, let's go do more complicated stuff. But there's no point if you can't even get the simple thing right. To look at all
Mhm.
these complications and extra dimensions and like, yeah. So, yeah, there's another one that I looked at many years ago before all this. This is like ancient, when I was starting to question things. I was just looking at other models, and there's this model, the Lesage shadowing, where the idea is that
Mhm.
their gravitons are constantly flying around, right? So the idea is a totally different model. That you have these gravitons flying through space. Again, the question is, where are they coming from? But anyway, they're all constantly flying. And imagine here they're flying from the left side here. And I think I do actually have a simulation also. This one. Yeah, it's not that great. It's been a little bit hard to see. But you have these gravitons flying around. And when you look at the forces, right? So as these graviton particle bump into some object, it gets pushed around a little bit. But the thing is, because there's a shadowing effect, because in the middle here, there's fewer particles, just like similar to the Casimir effect, I guess, a little bit. You would then the resulting force would tend towards the center because the space in the middle is a bit shadowed.
Yep.
So
Mhm.
and yeah, that could explain some of it, but
Yeah.
but there's no explanation why would clocks slow down, or what about
Mhm.
lensing and bending? Where are they coming from? It's an interesting model, but I don't think it has any
No, I
real,
don't.
but there's some people who, and I think it's good to come up with ideas. I think
Yeah.
it's really important, even if it turns out to be not the correct model ultimately. So yeah, I mean that's basically all I have right now
Okay.
on general relativity. So it's really not that
So,
different. And also to be fair, I know some people complained, like one person was saying, well, of course, there's something real to it, right? And that's true. I think most scientists would probably agree that space-time is not only geometrical, but the thing is still, they stop asking the question, what are its
mhm.
properties? So even
Yeah.
though a lot of people will agree, yes, it's a real metric, there's something real to it, why not? Is that step so large to ask, well, if it's real, let's ask one more question.
Yeah.
What's the property?
What is it? What is
Like,
it?
but that's taboo. Oh, no, no, you cannot ask that.
Yeah.
Oh my
I
God. Oh
know.
my,
It's
how
crazy.
could you? How could
Yeah.
you ask? Like, this is the only difference between, yes, it's real, and let's ask one more question. So, which I don't know why people, this step is so large for some people. I
Yeah.
think it's natural. I mean, I don't know. I don't think it's super crazy to ask this question. So that's really the only difference, because once
Yeah.
you have a property, you have elasticity or density, then you get all of this automatically. You
Yeah.
get refraction. Um, you get the metric tensor can be explained easily. Also, once people realize this is really not that complicated, we can actually use the research from material science to investigate this further, right?
Yeah, exactly.
I mean, people
And
have
they
probably
do
studied,
like
yeah.
for black hole model, they've got I think it's Penn State University is modeling black holes using water flowing down a drain. And this is a real, they call it the black hole lab. Like they're
Oh,
literally
yeah.
using another analogy, which is a fluid analogy, to talk about black holes. So I think it's a good idea to have ponderable real analogies to maybe discover new features of black holes that we didn't think of before if the analogy is good, right?
Yeah, exactly,
So I
exactly.
did a bit of a deep dive with ChatGPT
Hmm.
after we decided we're going to do this next video. And so I'm just going to read a couple of things and because it's saying that it's a good analogy
Hmm.
to a point, okay? I think you've addressed all the points actually. So the main one that it said that so historically they've used this refractive medium. They've tried to use the refractive medium, but there was a factor of two problem. So it said historically, if you treat gravity purely as a refractive medium in flat space, you only get half the correct bending of light. And so
Hmm.
this was a big deal. Early attempts predicted half the observed
Do you
deflection.
have a paper? Is
Okay.
there a reference? Because that's something people.
I could get a reference. No, I don't think it's a problem because so then it said because in GR light bending comes from both space curvature and time curvature,
Uh-huh.
which I think you dealt with in your
Yeah.
model.
Hmm.
I think you
Yeah,
dealt with
yeah,
that.
yeah,
And
yeah. I
so
mean, in
they,
time
in
is
my
yes.
opinion,
Mm.
the optical analogy, so he said the optical analogy only captures space curvature, but I think you did it correctly, right? I think you actually did deal because your clocks slow down
Well,
in
yeah,
your
if the
the
light wave
medium,
slows down, automatically
right?
clock slow down. Of course,
So,
if you
it
don't
said
consider that, you get the problem. Yes, of
yeah.
course.
So, time is doing something. So locally the speed is always c. So I think you've addressed all these issues. And so I
Mm.
guess the thing would be, is there a way to test your model to make sure that the curvature is exactly what the curvature that relativity predicts? I
Yeah.
think it would. I think it
Well, I
would.
think I would, if someone really wants to dive into this, there are papers,
Yeah,
right? So Robert Close, and for his website is not very great. It's like just gray and gray. He's not very good with communication like this.
yeah.
But
So,
it's
but
very, very, he's a very
yeah,
serious guy, and he too modest actually. He's way too modest. His work is really fantastic. Okay, the
yeah.
thing is, his papers are very mathematical. He will not
Hmm.
bother with images or anything. He
Yeah,
will just have
yeah,
formula, 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 formula. So that's why it's
yeah,
really hard for people. Even like it was for me, it was really hard. Thanks to also AI, it helped me to understand it better. It's not the kind of thing you read on the weekend for fun unless you're really into this. So that's why I'm trying to explain this more visually. But if you really want to know the math, it's there. It's just,
yeah.
and I will put the links in the
And
description.
you're using that math in your models or
Yeah, of course, I'm using the
yeah.
math, but
Yeah,
in most
exactly. Yeah.
cases, it doesn't. I don't even. It doesn't matter if the last decimal point is correct. It's more about how does it work, right? Whether this is a zero point 0.1 error, it doesn't matter because it's the
Yeah.
same concept. It's the idea that the idea of how refraction works in general, right,
Yeah,
and all that. So it's just
exactly.
I'm trying to
So
communicate how it
ChatGPT,
works.
yeah,
Yeah.
said that an optical medium doesn't naturally explain why clocks run slower in near a mass in this refractive index, but you clearly explained that.
Yes.
So,
You should tell
you know,
GPT. Yeah, you should
I'm
tell
really kind
GPT
of
about it.
wondering why, again, you're wondering why this hasn't been done before. Well, they did it before, but they did it incorrectly.
Mm-hmm.
And they got the wrong, curvature of the light going past the sun, say, or that sort of thing. They got
Yeah.
half the value. They didn't take time into consideration, but it looks like you are taking that
Yes,
your
yes.
model can explain why clocks slow down.
Oh, yeah, it's obvious,
Right?
right? Because the light
So,
speed is lower
yeah,
in a higher density medium. Yes.
yeah,
Mm.
yeah. And so
Yeah.
that's what I got when I rewatched your video again last night because I had these questions I was going to ask you, and
Mm,
then I
okay.
realized, well, obviously you would address these issues in your
Hmm.
model. And
Yes, yes.
so I would expect that your model would
Hmm.
predict the correct curvature because you're using you can see the whole metric tensor in your model.
Yes, yes. And in fact, if you Google optical analogy of general relativity, there are many papers. People have been working on
Mhm.
this. People have been
Yeah.
using general relativity and applied it to material science.
Mhm.
So this is well known. There is this optical analogy is known. People have
Yeah.
been using it so that's why when I first saw this, like, why don't people discuss this more? It's
Yeah. And I'm also surprised that ChatGPT kind of is pushing the narrative that
well, it will always push the mainstream. So it will
this
always,
factor of
always,
two
always,
the
it will
factor of
always push
two
the
problem
mainstream.
is called the
Yes, yes.
factor of two problem. So it's got a name. a factor of two problem. And but obviously your model.
It might be made up though. Like some the AI
That's
is
true.
really.
That's
I would
true.
just
That's true.
ask it
I've
for
heard of this
reference,
before, though. I've heard of
and
this before, though. So I wasn't
yeah,
surprised
yeah,
that
yeah.
it
It's
said this,
possible. It's possible.
but
Hmm.
yeah.
Yeah, yeah. Yeah, and that's actually, in a way, the next topic will be special relativity is even easier. Really, I think one line is you can really summarize it with, well, obviously a moving clock, runs more slowly because it has a longer path, but it seems that's not obvious to many people. So I have some more demos also to explain this, hopefully really clearly, because I think once you really see it, it's like, duh, it's obvious.
Yep.
And yeah, 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 hopefully.